All right, so as Brad mentioned, today I'm going to be talking about a little bit about, I actually put a lot of the different stuff that I've been doing over the last 11 years here in Minnesota into a 35-minute presentation. So buckle up, we'll talk a lot about all sorts of things. And one of the things that has been already mentioned today quite a bit is the fact that climate change is really making it very difficult for us to make substantial improvements in nitrogen management. We may be doing things way better than what we used to, but weather really is playing a major factor in undoing some of those things that we are trying to do better. We are having warmer temperatures, especially in winter and spring. And then weather conditions actually at the wrong time of the year. Spring, they're becoming wetter, and then as we saw last year, the prediction is that summers may become drier, which is also a problem. And all of that combined creates major issues for nitrogen management because we basically have more potential for nitrogen loss and maybe not as much nitrogen availability when we actually need it for the crop. Now, one of the things that I want to talk about today is some of the things that we're trying to do with management and kind of present some of the challenges that we are finding. Okay, I think for a lot of the people in this audience, these things make sense, but I think it's important that we actually talk about them because we tend to, I think as the industry has moved to this 4R concept, it's great for people that understand nutrient management, what we mean by the right something, but there are other groups that don't really understand that. And then when they hear something like the right rate, they say, well, if you know what the right rate is, why are you not applying it? And so today during the presentation, I'll be talking quite a bit about some of the challenges, the real world challenges that we have in terms of determining what that right thing is. So this is a soil sampling that we did a few years back, where we basically did 100 foot transect across a field, and we collected soil samples every 6 inches across that transect. And we kept each of those soil samples separate, did the analysis for ammonium and nitrate, and these are the results that you see here. The red is for corn as the previous crop, the blue is for soybean as the previous crop, and we had both drain and undrained conditions. This was a poorly drained soil that had tidal drain, and it was either open or completely closed to create these conditions. And you can see here across the transect, total inorganic nitrogen in parts per million, and you see that even within 6 inches of difference between one sample and the next, there is quite a bit of variability, and that variability was actually even bigger if you have poor drainage in those soils. And so this is real life. This is what you see in real life. It's not a uniform thing that we are dealing with in the field. And of course, this is micro variability because nobody's going to be sampling every 6 inches a field, right? The other thing that we did in this study was to calculate how many samples you would need in a composite to know with a good level of certainty that the value that you get from the soil testing lab is accurate for that field. And we determined that you need at least 20 cores into a composite. Tell me, how many of you are excited about taking 20 cores to determine, and this is, you know, on a 2.5 acre grid or something. Nobody will do that. And so those are some of the challenges, okay? That we deal with. There's a lot of variability out there. We did some work also looking at the pre-site nitrate test as a tool that we may be able to use to manage nitrogen better. This is what, and Dan mentioned some of these things today. So this is the data. This is across 34 field experiments. You can see all of the data, and we do get to about 20 parts per million is where we would say don't apply any nitrogen. But you see that in a model, if you look in the model, they probably present something like this, a nice little line. But you see the data, it's all over the place. It's not as uniform as sometimes we tend to think. Okay, so there is a lot of variability there. Yes, you can use that regression to determine what that point, that optimum point is, but there is a lot of variability there. And then we also looked at how much nitrogen would be available or would need to be applied if you have a suboptimum amount of residual nitrogen. If you're below that 20 part per million, how much you would need, and this is what that data looks like. And again, you can do regression, you can look at these things, and we determined that, you know, for to increase the soil test value to 20 parts per million, if you're below that, you need to apply about 12 pounds of nitrogen per acre to increase the parts per million by 1. But again, quite a bit of variability on that data, okay? And this is real data, this is real world data. That's what we are dealing with. So when we are talking about uncertainty, this is what we are talking about. Is there is a lot of stuff there that creates uncertainty. And then you add different uncertainties and those tend to compound. And so it becomes more and more uncertain as you move on. We talked quite a bit today about soil organic matter and the value of soil organic matter because it produces nitrogen. It gives us quite a bit of nitrogen. And this is looking at the amount of organic matter from 0 to, you know, higher organic matter, and then the potential mineralizable nitrogen. So this is under ideal conditions in the lab. We took all of these samples across Minnesota, analyzed them under ideal conditions on how much nitrogen you can potentially get out of those soils. And you get a really nice linear relationship right there. You know, as you increase organic matter, the amount of potential mineralizable nitrogen increases. But I highlighted here a couple of examples where the amount of organic matter is exactly the same, but look at the difference in terms of potential mineralizable nitrogen, substantially different. And you look at these soils, they were the same kind of texture, the same amount of organic matter. Everything seemed to be really similar, and yet the results were extremely different. So again, another component where we have quite a bit of variability that we cannot really well determine or predict. This is a study done by one of my students using M15, and nitrogen 15 allows us to determine basically the nitrogen that we are seeing, whether it's in the plant or the soil, where it came from, because it has a label, okay, an isotopic label that allows us to track that. That is not from the soil organic matter, but it's from the fertilizer that we actually apply. And so what you see here is the potential, the fertilizer-derived nitrogen in here, and what happens with different nitrogen rates, okay? We apply nitrogen, and then we went there within about 7 days after the application to measure how much nitrogen was present. The red or brown color is total inorganic nitrogen. The blue is the organic or fixed nitrogen. So in essence, 85% of the nitrogen that we apply as a fertilizer, about 7 days later, was gone as far as the plant was concerned, because it was not in the inorganic form. It was not in nitrogen, in ammonium or nitrate, but it was in the organic or fixed form of nitrogen. So quite a bit of that nitrogen, it just basically is not there right away for the plant. And then as you go to the growing season V8, R1, post-harvest, you can see those values. Regardless of how much nitrogen we apply, the different rates are in this axis right here. We also have split application with those rates pre-plant and then split. But the point is that the majority of nitrogen that we apply is rapidly immobilized or fixed in the soil. It doesn't mean that it's gone. And this is also something that is important for us to consider. Typically, when we talk about nitrogen, we say, well, if it's not in the plant, it's lost to the environment. And the reality is that it's not lost to the environment. Quite a bit of that nitrogen remains in the system, but it's just not available to the plant. And we need to continue to do some work on this. The other part too is, so this is again continuing to look at this M15 analysis. We are looking here now at nitrogen in the plant. And so this is the fertilizer-derived nitrogen and the soil-derived nitrogen. Here, again, because of that labeling, we are able to know how much of that nitrogen actually came from the soil versus the fertilizer that we applied. This is a V8. This, again, different nitrogen rates. This is the equivalent of a single pre-plant compared with a split application here. And you see that early on in the season, the plants tend to use quite a bit of nitrogen from the fertilizer. As the season progresses, more and more of that nitrogen comes from the organic matter, from that mineralization process. And of course, some of that N15 probably was immobilized and then mineralized and the plant used it. But again, the majority of nitrogen is actually coming from that organic pool, that it's not the fertilizer that we apply on that year. All right, so with that, you say, well, there is quite a bit of nitrogen. Quite a bit of that nitrogen is not available to the plant that year necessarily. What is the contribution of organic matter? And so this is from the MRTN database that we have for Minnesota, looking at the check plot where we apply no nitrogen and how much yield we got out of that, out of those plots. And so here you have a corn yield. These are the number of sites and different rotations: continuous corn, soybean, 2 years of corn followed by soybean. And you see here the yields, that the range goes from 52 bushels to 218 bushels per acre produced with no nitrogen. Okay, so that's another level or layer of variability. That's on average 100, we get 116 bushels of crop produced. If you estimate approximately how much nitrogen it takes to produce a bushel of corn, just doing a quick calculation, this is how much nitrogen you have: anywhere from 58 to 240 pounds of nitrogen produced through mineralization on a given year, and this is across the state. Okay, so again, another layer of variability that we have to deal with, that makes it really difficult to say what is the right rate. Okay, because it could be 0 or it could be 200 pounds that we are getting from that soil. This is another example of dealing with variability. This is looking at different years, 9 different years, and the optimum N rate in blue and the grain yield at that optimum N. And you can see what that is. We can do an average across all those years. That will be right here. This is the mean nitrogen rate. This is the mean yield for all of those. But if you see, it's like from one year to the next, you could produce the same amount of yield with substantially different amount of nitrogen needed. And other years, you produce substantially different yields with about the same amount of nitrogen needed to get to that optimum. Okay, so that variability is what we are dealing with, and it's difficult. It's how do you predict it? I mean, we try to throw everything that we can. Sometimes I'm getting convinced as a researcher that perhaps it's better to look at fewer variables than more variables, because when you look at few variables, then you can always say, well, we didn't really measure that, so that's probably why we could not explain the variability. But when you start putting everything you can think of into the experiment to measure and you're still coming empty, it's like, what can I attribute it to? I have no idea. I measure all of these things, and yet I still cannot explain that variability. This is another example. So this is a long-term nitrogen study that we are doing across the state in different locations. We have one here at the Lawler farm, where we have continuous corn and corn soybean in a lot of these locations. And it's a fairly small plot size when you consider large-scale agriculture. For a small plot research, it's actually a fairly good size study. So 2 acres in size, and what we have is 5 nitrogen rates that go from 0 to 240 in the case of corn soybean. The rates are higher for continuous corn. And within each one of these, basically what you have is 6 subdivisions of 4 row plots, basically. So you replicate that 4 times across, and so what you end up with is 6 nitrogen rates replicated 4 times, okay? And with 6 repeats. And you end up with 6 response curves to nitrogen that have replication, so you can do statistics with it. And with each one of those, you can determine what the economic optimum end rate would be for that particular subset of 1 to 6 subplots, okay? So we did that. This is across 12 site years across Minnesota. And in those 2 acres of plot size, what we find is that the economic optimum end rate varies by 47 pounds of nitrogen per acre, okay? And now we're talking about only 2 acres. Doing everything right, measuring exactly to, in grams. We measure the amount of fertilizer we apply in every single plot. So we know that we are applying the right amount, everything is right. And yet we see that the economic optimum could be anywhere from, minus 27 pounds to plus 19 pounds from the average of economic optimums, okay? And this is on 2 acres. Remember, it's 2 acres. It's not a large field. And so that's additional variability. Everything in those fields is exactly the same. The soil is the same or fairly close. The weather for that year is exactly the same for that whole crop. Everything is the same, and yet the response that you get to nitrogen is, about 30-pound difference there, 47-pound range. So that's additional variability that we have. And so Dan shows some slide like this today. This is from the MRTN calculator. This is for corn after soybean. You have the average and then the range of nitrogen when you do the plus minus $1 per acre. And we have this distribution of, the MRTN for all of the sites across the state. And so you can see that this is the range of plus minus $1 per acre. If we apply the data from that study, okay, you will be looking at a much larger range of 115 to 161. And so that's the reality, is that the database that we use for the MRTN calculator has variability. That's why you see this distribution graph like that. And then when you put something like a smaller scale, like a 2 acre scale, that tends to even become bigger. And so those are the kinds of variabilities that we are dealing with. And so while I would love to say, we can manage nitrogen down to the pound, the reality is that if we are managing within about 30 pounds of nitrogen on a year in and year out, we are actually doing really well, okay? I wish it would be better, but that's the reality. That's what I keep finding through a lot of the research that I do. The other thing is, in terms of theory versus practice, is residual nitrogen, so and the environmental impact. And we've seen some of similar graphs like this. This is the theory. You apply nitrogen, you increase yield to a point, and then it plateaus. And then in terms of nitrogen loss or nitrogen left on the soil, you have fairly little difference between the optimum and below that optimum. And then we start to increase the amount of nitrogen loss potential or residual nitrogen as we increase nitrogen above that point of maximum or optimum yield. In reality, we find that it's actually pretty accurate, which is great. That's not always the case. This is actual data where we see the increase with nitrogen to an economic optimum. In this particular location, it was 121 pounds. And then you look at the residual nitrogen, this is in the fall, and you see that there was pretty much no difference between no nitrogen applied to that optimum. And then once we went above, where basically corn is not using any more nitrogen, it's kind of a pound per pound of nitrogen. All that nitrogen that we applied extra stays there as a residual. The challenge, of course, is that the soil is not a very good place to store nitrogen. And so this is the same sites the next spring. And you see that there was not much change in here in the amount of nitrogen residual from the fall to the spring, but this larger amount of nitrogen in the fall is not there the following spring. And so that's why we talk about the importance of targeting that optimum nitrogen. As hard as that would be to determine what that optimum is from year to year, using the MRTN calculator gives us actually a pretty good idea of where we will be within the ballpark, okay? And like I say, if we are doing about around 30 pounds around that, we are actually doing pretty well. And so that's what we are talking about in terms of productivity and also in terms of environmental protection. We are not going to improve the environment by reducing nitrogen below what is required by the crop, but we can do a lot better if we reduce nitrogen from excessive nitrogen to that economic optimum. This is another study looking at it perhaps in a different way, where the economic optimum is equated to 0, and then we have fall and spring residual soil nitrogen in the top 3 feet of the soil. And again, you can see that if we are at the economic optimum or below, there's not really a lot of difference between fall and spring, and the residuals are pretty low. But then if we go above that point is where we start to see this substantial increase in residual nitrogen, which by the following spring is basically the same as having applied no nitrogen or a suboptimal N rate, okay? All right, let's talk a little bit about the right time of nitrogen application. Again, people look at this and say, well, if you know what the right time is, why are you not doing that? There are a lot of complicating factors, again, on these things, and I think it's important for us to recognize some of the challenges. In theory, we know that the annual rainfall pattern dictates the leaching potential of nitrogen. We also know that this tends to be, the highest point tends to be before corn really needs a lot of nitrogen, so early in the spring. And we know that because corn starts to take up nitrogen later in the season. And so in theory, you would say, well, instead of applying nitrogen here at the beginning of May, let's look at, the beginning of June. So it's past this point of high potential for nitrogen loss and before corn really starts to need a lot of nitrogen. In theory, that looks great. The reality is, and some others have talked about this, is that it doesn't always work out that way. This is a study we did across the Midwest. So there were sites from Minnesota, several sites from the southeast part of the state, and other regions in the Midwest, where we were looking basically at pre-plant versus split application of nitrogen, and then we looked at those splits where the split was the same as a single pre-plant application, or a split was less than a single, or the other way around. And we had 2 rates of pre-plant or the split application, either 40 pounds or 80 pounds of nitrogen. So in here we are looking at the 40 pound, the yellows are for 80 pounds pre-plant, and then the rest are side rest. And this is the percent of sites where we saw these particular situations. You can see that 80 to 84% of the sites, the split application was the same as the single pre-plant application. So the majority of sites, it didn't really matter whether we were pre-plant applying or split applying nitrogen. In some situations, it was better to do the split application, and in some situations, it was better to do a pre-plant application. But those were really specific to very specific conditions. For instance, the split application was always better in sandy sites. But all the other soils where we have, fine texture soils, there was basically no difference, okay? So in theory, you would expect that will help us manage nitrogen better, and it can, but in general, you are not going to see that response year in and year out. It may be a specific situation. Last year was a perfect example. There were better responses with split application last year than pre-plant application in a lot of situations. Why? Because we did have a huge amount of rain and a huge potential for nitrogen loss. But it was kind of a normal year when it comes to that. And so very specific conditions can help us, but in general, those split applications don't always give us the answer. And sometimes I think that when we tend to simplify these things, we shoot ourselves in the foot, because people that don't understand agriculture, they look at these things and say, well, why are you not split applying nitrogen all the time? It works better, right? Well, no, it not necessarily. In certain situations, it might. And then that data where we looked at the pre-plant versus split application, this is all of that data put together. What you're looking at here is the 0 will be the economic optimum, okay? And these are all the data points for the different styles we had. We divided the data into different things, but the important thing here to recognize this is the total nitrogen uptake at R6. And you can see that the two lines for split or pre-plant only applications are on top of each other. So it basically made no difference as far as the plant is concerned in terms of how much nitrogen the plant needed. It didn't make any difference whether you were pre-plant applying or split applying nitrogen. The response was exactly the same. And then this graph is showing the residual soil nitrate at the end of the growing season. And you can see with the dotted line here, this is for the split application, that as I showed you earlier, if you are at the economic optimum or below, there was very little residual nitrogen. And then once we started going above the economic optimum, we started to increase the residual nitrogen. And there was actually more residual nitrogen for the split application than the pre-plant application, which would be counterintuitive to what we've been talking about, that in theory, you should be able to use nitrogen more effectively. Well, the data here shows that the plant is no more effective at taking nitrogen when you split apply, and you actually end up with more residual. Now, when you look at the residuals, you may say, well, a split application, then it's worse. I would say, no, the problem or the difference here is when you lost nitrogen. With the pre-plant application, you probably lost some of that nitrogen early in the season. With the split application, at the fall time, you still have it there, but it will be gone by the next spring, as I showed you earlier. Another study, so looking at, again, we're just trying to look at all the kinds of variables that impact nitrogen to see if we can understand how to manage nitrogen more effectively. In this study, we were looking at pre-plant versus split applications of nitrogen for different years, from 2014 through 2019. And what you have here is drained and undrained soil. So this was the same soil with or without the tile drain. They all had tile drains. Half of the plots were with an open tile, half of the plots had the tile completely closed. And so drain and undrain, the economic optimum end rate, and the yield at the economic optimum for all of those conditions. And what we found, 2016 was a really good year for crops in this particular location. This was at Wells, Minnesota. That in good conditions, it didn't really make a difference whether you had adequate drainage or poor drainage. The yields were pretty similar. The economic optimums were pretty similar. And the split application versus the pre-plant application made very little difference. Okay. Then we have this year where it was really wet. I don't remember now, but it was like we had something like 7 inches of rain during June. It was just a really wet year. And in those wet years, the drain conditions made a huge difference. When you have those conditions, having adequate drainage is important. It reduced the amount of nitrogen that you needed to optimize the crop and improve the yield. And the split application was better than the pre-plant application, especially if you had poor drainage. Okay? Why? Because you have more potential for nitrogen loss under those conditions. And so split applying nitrogen later in the season makes the most sense. The challenge is that we never know when we start the season and when we need to apply nitrogen, we just don't know what those conditions will be. And so the split application can help us, buy us a little bit of time to know what the growing season was up to that point, but nobody knows what's going to happen later in the season. And then as an average across all of these years, we find that regardless of the drainage, we find that the drain system improves nitrogen use efficiency by the crop. We reduce the amount of nitrogen needed to get to that optimum compared to undrained soil. So having adequate drainage is very important. The other part is that in terms of the pre-plant versus split application, in general, again, as I mentioned earlier, it did not make a difference. It was related to specific conditions. Those really wet conditions or conditions where you have poor drainage, that's typically where you will see an advantage with the split application. All right, and then I put all of that data together in terms of yield in terms of nitrogen, residual nitrogen. And what we found is that this is looking at total nitrogen in the system. So we are looking at total nitrogen in the plant plus whatever is residual in the soil. What we found is that under drain conditions, we do better with nitrogen, okay? And the interesting thing here is, again, when you look at the water quality, people would say, you know, having tile drain is a problem. Why? Because we speed up the movement of nitrate from the ground, from the soil, down to a stream down to the river. And that's true. But when you look at it in terms of, okay, if I don't have adequate drainage, you actually are doing worse for the environment for two reasons. One is because you're actually losing more nitrogen. In the undrained system, we needed more nitrogen to get to the optimum. We had less nitrogen accounted for, so we lost more nitrogen. We were not as efficient. And economically, we were worse off because we produced lower yields. And so when we look at the drainage conditions, I say, take you to poison, is pollution swap. When you need drainage, if you don't have adequate drainage, you are going to lose more nitrogen through denitrification, which if you're only focused on the water quality, you'll be happy because it's like, oh, we improve water quality, we don't have as much nitrate. The reality is that we are in a closed system in this world that we live in. We might not be losing water through or nitrogen through nitrate, but we are losing it to the atmosphere, which is creating more issues in terms of greenhouse gas that creates global warming and some of those changes that we are seeing in terms of climate. So it's never a all or nothing. Is which one is the word? Which one do you want to use that will be the least evil of the options, right? You are going to lose nitrogen. If you're going to produce crops, you're going to lose nitrogen. Trying to improve management so that we minimize that is what we need to be putting our thoughts into. So this is another study where we were looking at the kind of a combination of factors, looking at source, placement, and timing. This is from southwest Minnesota, so different conditions than the southeast, because we do have tile drain in there. And it was a Webster clay loam soil. We did this study over 7 years, and we had 4 treatments. And again, what we are looking at here is what can we do to improve nitrogen management. So we looked at urea pre-plant as kind of the standard practice. And then we had 3 other treatments, ESN, which is a polymer-coated urea, and then these 2 that were split applications with 60 pounds of urea or ESN pre-plant, and then 120 pounds with urea plus agrotain as a side dress at V4 to V6. So 2 treatments with pre-plant application, 2 treatments with the split application, and these 3 treatments here were basically being compared against the standard practice of urea. All of these were all at 180 pounds of nitrogen simply because we only had a limited number of plots where we could look at these things. These plots, the nice thing about these plots is that they have a perimeter around them with a curtain buried down 6 feet so that the water that comes out of each of the tile lines into these receptacles, it allows us to measure basically all the nitrogen that is coming out of that treatment, of that plot, and also the volume of water that allows us to calculate the load of nitrate coming out of each of these treatments. And so what we find here, so this is just 1 year of data to show as an example. There's a lot of the information here. So we have the 4 treatments here. This is a cumulative nitrate leaching across the growing season. And from April through November, these are the 4 treatments. This is the split application or the pre-plant ESN treatment. And then the dark green is urea pre-plant, and then these 2 are the split applications. The precipitation is here and is represented by these bars. So these are all the precipitation events that we have during the growing season. I apologize that these are in metric units, but the point is, it doesn't matter what the units are, it's just the point I want to make in here, is that if you look at the nitrogen loss, regardless of the treatment, it follows the same pattern. If you have excess rain, you have increase in nitrate leaching. Even with the best treatment here that had the lowest loss, you still see the same pattern across all of it. And in this particular year, I kind of pointed out in here, there were 5 events where we had the most nitrogen loss. And this is pretty typical of these systems. And the challenge of managing the nitrogen loss that we get. Because if that loss was continuous through the growing season, perhaps we could do something to manage that water, that nitrate coming out of the tile. But when you get these episodic events where you have a lot of water, there is absolutely no way to retain all that water and treat it or do something with that water to make a difference. And that's a challenge in terms of managing at the other end if we're trying to, protect that water from getting into the river, for instance. The other thing that is interesting out of this that I like to illustrate is that if you look across the growing season, there are kind of 3 periods during the growing season where in here we have pretty low vegetation, typically excess rain. Soils tend to be saturated or near saturation in the spring. And so any water that we get is excess water. At that point, that pushes nitrate down the profile. Then we go into this period where we do still have quite a bit of rain, but because corn is taking up a lot of water and a lot of nitrogen, you see basically no nitrogen loss. It's flat in there. And then later, as the crop reaches physiological maturity and is no longer taking nitrogen, and we start to get more precipitation, for a while the soil is able to retain all of that water because the soil is dry. But once it reaches that saturation point, water starts to move nitrate down, and that's what you see here. This increases again in the fall. All right, so this graph here shows the relationship that is there between drainage and nitrate loading. This line here represents the amount of water, so the drainage, and this is the nitrate loading for different nitrogen rates. And you can see the same exact pattern as the drainage with the nitrogen loading, okay? More water, more leaching, more loss, okay? And that's why I said that these changes in climate that we are observing are challenging, because we could be doing everything right in terms of the management that we do with nitrogen, but having that additional water makes it really difficult to make an improvement in what we actually measure at the end. Continuing on with this study from Southwest Minnesota, we also looked at not only nitrate leaching, but also ammonia and nitrous oxide emissions. And so here is kind of the 2 different years, 2 different stories. 2019, so this is looking at cumulative ammonia volatilization for those 4 treatments. Again, we found that the pre-plant ESN was the lowest. This is pre-plant urea. You can see that it increased pretty rapidly and then it kind of plateaus. And then for the split treatments, you see very little nitrogen loss here. And then here's where we apply the split application. That's the arrow here. This is when we apply nitrogen. And at that point, we apply the remaining nitrogen for those split treatments, and you see this huge increase in loss in 2019, which was not the case in 2020, okay? The big difference in here is how much water we got. In this particular year, we got just enough water to get that application into the soil, but not really deep into the soil. So that created ideal conditions for volatilization loss. And so even though we were doing a best management practice of split applying nitrogen, we actually increased the amount of nitrogen loss, not because we were doing anything wrong with management, but it was because we applied it at the wrong time. Of course, there is nobody that can tell you when it's going to rain and how much it's going to rain. And so trying to do everything right, getting the wrong results simply because of that. 2020, same type of management, the losses were reduced substantially simply because there was more rain, and that rain pushed nitrogen into the soil, so there was less volatilization potential. And then nitrous oxide, and this is 3 years, 3 different results. In 2018, we have, so this is a pre-plant ESN, this is pre-plant urea, and these are the split treatments. we had pretty high potential for nitrous oxide emissions early in the season when we did the pre-plant application, and we also had the same situation for the split timing, okay, represented by the arrows here. And so with ESM, we were able to manage the losses pretty well, but the urea pre-plant and the split treatments were not different. In 2019, we had pretty high potential for nitrogen loss through this denitrification process with wet conditions early in the season with the pre-plant application, and you see huge increase in losses with urea, but not with the others, because the split application was actually pretty good. There was no huge amount of rain that created, desaturated soils, and so it behaved pretty well. And then in 2020, it was a drier year, where it didn't matter when we apply nitrogen or what form of nitrogen we apply, the losses were pretty low. Okay, so again, same management, same everything, different growing season condition, completely different results. And so if you don't get anything out of this presentation, I hope you get one thing, that managing nitrogen to the best of our ability is what we need to try to strive to do, but then understand that the results, the ultimate results, will be depending a lot on what happens during that growing season in terms of weather, specifically rain. Oops. All right. This is for that study, all the cumulative losses. So I put it all together into one bar graph. Here we have the pre-plant treatments, the split treatments, and the amount of nitrogen loss, either as nitrate, nitrous oxide, or ammonia. And you see that compared to pre-plant urea, ESM pre-plant reduced losses by half. And that's really good. But the other thing that I like to point out is that 13 is not zero. Okay, so we reduced it by half, and that's a great accomplishment, but it's not zero. And this is also something that I think is important for everyone, society, farmers, everyone to understand, is that if we are going to produce crops, there will be an environmental impact. We can reduce it, but there will be an environmental impact. And then with these best management practices of split applying nitrogen, you see that there was no difference compared to the traditional or normal practice, okay? And so again, it's not that this best management practice was a bad practice. It had to do everything to do with when we apply the split application and what happened right after that in terms of weather. And in the study here, unfortunately, a lot of the years were conducive for nitrogen loss. And so we actually enhanced nitrogen loss by delaying that application to later in the season. All right, in terms of corn yield, for those 4 treatments, they all pretty much did better than the pre-plant urea. Some of these were not statistically different, but numerically better than the pre-plant urea. And the best one was the split application of ESM pre-plant and then side dressing later in the season. And then the question, of course, is economically, how does that work out? And so using the prices that you see in here, we calculated that. And these are the costs of those treatments across the top here per acre. And this is the net return compared to this treatment of urea. So even with 100% ESN, which nobody would really do because ESN is more expensive than urea, you still come ahead in terms of profitability compared to pre-plant urea. And then, of course, this split application was the one that performed the best. So you need to look into some of these things too. I think we need to continue to be looking at, okay, management-wise, we can improve, we can reduce nitrogen loss with this specific treatment, and we can actually do better financially, so why not do it, right? And then for environmental groups that are really interested in making sure that we reduce the environmental footprint of agriculture, we can start to use some of the data here to say, okay, we want a reduction of X amount, this is the difference that will cost a farmer in their pocketbook to implement some of these practices. How am I doing with time?
You're kind of off, but
Oh, well, quickly. So this is another study we are doing very similar to what we did in terms of nitrate, ammonia, and nitrous oxide, and what happens in terms of nitrogen rate. You can see this is the average across all of those, that we can determine whether the economic optimum is, and then with these kinds of studies, what it will allow us to do is to look at, if we reduce nitrogen rates below that economic, how much nitrogen loss reduction we will have, or how much we will have above that point. And again, being able to use that data to say, this is the real cost to producing crops, and this is the benefit or potential benefit if we reduce it below the economic optimum. This is the cost that will result on that. The question is, who would pay for that difference, right? Those are discussions that go beyond this presentation today. The last thing I want to mention is here that, again, not everything happens in the same way every year. When you have, looking at nitrate leaching, for instance, these 2 years were pretty dry, so the potential for nitrogen loss to the nitrate leaching was pretty low, but the volatilization losses were pretty large. In 2023, wet year, we substantially increased the amount of nitrogen loss through nitrate leaching, but there was hardly any through losses to the atmosphere. And so that's another important thing to recognize, is that we need to be careful in what we are looking at. Is like, if we are only interested in water quality, there are things that you can do, but the reality is that we need to be looking at all of these things, and they don't work in the same way. When you have conditions that increase nitrogen loss through nitrate leaching, you may not be losing as much to the atmosphere, and the other way around. And so those things are things that we should keep track of. And so key points here, I think we need to look at best management practices. We need to continue to try to use the best management practices, but we need to be cognizant that we are going to lose nitrogen, and then we need to find ways to manage that nitrogen loss so that it doesn't actually end up in the environment. And out of the 4 R's that we normally talk about, I think once you manage everything right with all the other 3 R's, nitrogen rate is the big one, because you do have to do all the others correctly, you know. But once you determine that, using the optimum N rate is the most beneficial, just because, as I show you time and again, once you go above that point of economic optimum, that's where you start to reduce your profit. You're not getting any more money from that application, and you're starting to create a bigger environmental impact. So with that, I will stop. And are there any questions? Do we have time for a couple of questions, maybe?
Take a question or two, we'll be all right.
The tillage practice for all of these plots is conventional. The question was about any correlation with covers. So I did not present data here with covers. We are looking at cover crops. And in general, for crop production and environmental performance of treatments, it typically makes very little difference. The biggest challenge that we find is getting the cover crop established in a way that it will make a difference. We do get the cover crop, but I would say probably, I don't know, if I had to look through all the years, maybe 1 in 5 years you get a cover crop that is established well enough to make a difference environmentally, that doesn't, produce a yield penalty for that cover crop.